Hey everybody, I hope you're doing great today. Let's go ahead and finish up our discussion with proofs with finally our last four rules. So remember just from the beginning, right? The idea with a proof is we're trying to show that for a valid argument, if we accept the premises, we would have to accept the conclusion. So that's what we're trying to do. We're trying to show how, through intermediate steps, we can demonstrate that if we accept premises, the conclusion would follow. And this leads us to our rules themselves, because the rules are what guide us through each and every step. Every step we have to take has to be justified or has to be about some sort of rule. So in particular, right, we looked at all these non-subproof rules, and the idea was, well, if I know this line and I know that line, I get this next line for free, right? It just follows. If I know that A leads to B and I know that A is true, I just have to know. It just comes for free that B is true. And then we started looking at some subproofs. That got us a little bit more nuanced, right? The idea was we were going to say, okay, temporarily, I don't know that P is true, but let me imagine that P were true, show you what that results in, and then we'll step away and see what we learned, right? So if I show you that P leads to Q, it's not that I've shown you that P is true or that Q is true, but I would have shown you that P does entail Q. Right, so that's been our rules overall, and now we have two final subproof rules that we want to add to this. Right, two final ways in which we can justify a new line by first making some sort of hypothetical stipulation, just to see what is it that follows from that sort of hypothetical stipulation. Right, so that's what we're going to do in order to introduce negations first. Right, so suppose that I wanted to prove that A was false. Right, I want to prove that not A. That you should not believe that A is true. And why? Well, because if A were true, it would lead to something crazy, right? Maybe this is one reason why I'm not going to believe that A is true. So for instance, I might say that, well, if A were true, well, then that would lead to B being true, but it would also lead to B being false. And of course, that's a problem, right? Like, B can't both be true and be false at the same time. So that must mean that A isn't true. Because if A were true, then it would have led to B being simultaneously true and false. So this is what it means when we say we're reducing it to absurdity. So, right, this is one of the most popular like proof approaches, especially like as you go into other fields like math or science or all these sorts of things. One of the things that we'll do, one of the things that's common to do is say, reduce it to absurdity. Show how the reason why we're not going to believe in this particular claim or theory is that it entails something that's just nonsensical, right? If I accepted this, then I would have had to believe that both snow is white, but it's not white, right? If I had to accept this, then I would have to believe that both the earth is round and it's flat. That must mean that that stipulation in the first place wasn't true. Right? So that's what we're going to be interested in, right? We're going to be trying to show that we can make an assumption, and based on showing that that assumption leads to something ridiculous, we should reject that assumption in the first place. So in this case, right, I might say that, okay, I want to prove that A is false. So I'm going to assume that A was true. And based on assuming that A is true, I know, well, then that must mean B is true, right? That's just a easy conditional elimination from lines 1 and 3. B has to be true. But also, right, line 2 and 3 tells me that not B has to be true. That must mean that based on this assumption, I should be believing that B is simultaneously true, but it's also simultaneously false. But of course, that's what we call a contradiction, right? If you remember from when we started off doing truth tables, whenever you have something that's, yes, this is true, but no, that thing is not true at the same time, that's automatically false, right? Anytime you have something of the form phi and not phi, we know that that's false, right? If you tell me that, right, you have a dog, but no, you don't have a dog, well, then you are wrong to say that conjunction. Right? If you say, my name is Sean, but no, it's not Sean, right? Then you're wrong. Either your name is Sean or it's not Sean, but they both can't simultaneously be true, right? This is the law of non-contradiction. If we can show that some assumption leads to something that's just purely impossible, then we know that that first thing couldn't have been the case. Right? Because it would have led to something that's impossible. And because impossible things aren't true, that's the point, then we know the original thing couldn't have been true. So that's the spirit of negation introduction, right? Also known as proof by contradiction, right? We're saying that if we can suppose some assumption leads to a contradiction, then we know that that assumption was bad in the first place, right? This is an extremely popular way of proving things, both in logic, but also in math and sciences all over the place, right? So in this case, right, we showed that assuming A leads to a contradiction, B and not B, right? So this thing would lead to this thing, which is never true. That must mean this thing is not true, right? So that's the idea for proof by contradictions, for negation introduction, for reductio ad absurdum, right? Our Latin name for it. Right? There's all these different names because of how common this thing is. You're just assuming something purely to demonstrate how it leads to problems, just so you can turn around and say, see, that's why I don't believe in it in the first place. Right, so let's look at an example. We can look at that same sort of example, but with just different letters, essentially, right? P leads to Q, but P also leads to not Q. Therefore, we should say not P at the end of the day. So we can see the same sort of thing, but in our program now. So what I'm going to do is, I want to show that not P is true, right? I want to show that P is false. So I'm going to say, okay, imagine that P was true. Right? Imagine that P was true. And what I'm going to do is I'm going to show you that that leads to a contradiction. That leads to Q being true while Q simultaneously not being true. Right? So if we assume P, well then I know, based on P being true and P leading to Q, then I could do my I could do my conditional elimination. Right? Well, I'll take this, I'll take that, I'll execute, I got Q. But now I can also do another conditional elimination, right? Where I can say, okay, based on the second conditional, but P again, this time it's going to lead to not Q. And so then all I'm going to do at the very end, right, is I'm just going to point out. I'm going to say, see, there was a contradiction. You had me on one line believing Q, and then on the other line believing not Q, right? And that is a contradiction. Right? And so because of that, because we're able to show that P really does lead to this contradiction, then we should turn around and we should say P is not true in the first place. Right? And so that's what finishes our proof for us. So what we've shown here is that P leads to this contradiction, Q and not Q. And so because P leads to a contradiction, we turn around and we say, okay, P must not be true in the first place. And that's what our goal was. So let's look at this example, which might feel a little bit more involved actually, because here what we're going to do for the first time is start to look at some nested subproofs, right? So the idea is I'm trying to prove this conditional, right? So I'm not going to be thinking about proof by contradiction or right, negation introduction is what I mean by that right away. Instead, I'm proving a conditional. So that's what I'm going to do. That's what I'm going to think first, right? Right, if I look at my premise, I can't eliminate my conditional up here because I don't have P sitting alone. So I can't do anything with my premise. But down here I can see, okay, I need to prove a conditional. Let's do it. How do you prove a conditional? Well, you do a conditional introduction, right? Where you say, well, the thing that I want to start with is, well, let's think. What do we want to start with here? If you're thinking to yourself, oh, it's P. No, wait, back up, right? I'm trying to prove this conditional down here. I'm not, right, if I'm doing a conditional introduction, I'm not thinking about my premises like at all. I'm just thinking about what is the conditional I'm trying to build. And the conditional I'm trying to build starts with not P, but also not just Q. It starts with not Q. That's what we need to start with. So that's what we'll do. We'll say, okay, what we need to do is we need to show that not Q is going to lead to not P. That's what we need to show, right? We need to show how not Q will lead to not P. So we're assuming not Q, and we're going to try to get it down to not P, right? So that's how this subproof is structured. And now again, you might think like, oh, wait a second, what am I supposed to do now? Because like, again, I still can't do my conditional elimination because I still don't have my P on one side. But I can't do a negation elimination either. Why? Well, because negation elimination, remind yourself, right? It needs two negations at once before you can cancel those out. I can't just pluck a single negation off, right? That doesn't make any sense. I can't say, because I know Q is false, it must be true, right? The only way negation elimination works is if you have two negations that you can cancel out. So here it might feel like I'm kind of stuck. I need to come from if P then Q and not Q and somehow prove not P. But I can't do any of my elimination rules to what I already have. So instead, I need to think about what I'm trying to get to. And what I'm trying to get to is not P. So now we can think about this negation intro. Right now we need to think about, all right, we're trying to prove P is false inside this other subproof. Right? So that's what we're going to do. We're going to say, okay, let me set up a subproof inside this subproof. So inside of the hypothetical we already have going on, we're going to do another hypothetical. We're going to say, okay, now we're already supposing not Q is true. Let's suppose something else. Let's suppose that P was actually true. And then what I'm going to try to do is I'm going to try to convince you that that'll lead to a contradiction. Right? So I'm going to actually just delete these lines because I don't need them. Right? Let me zoom out just slightly so you can see this a little bit better. Right? So the idea is we have this nested subproof. Right? How am I justifying that not Q entails not P? Well, I started a subproof that starts with not Q and it ends with not P. How I fill that in, right, is just another question I need to answer. The subproof itself, right, this rule doesn't really care how I fill it in. Maybe I need to fill it in with like some and introductions or some and eliminations. Maybe I need to do more subproof. It doesn't matter. All that this main big subproof cares about is that it started with not P, or not Q, and it ended with not P. And that's how we show not Q leads to not P. And now when we step inside of that, now we need to just ask, okay, cool. Everything is open to us. How do I prove not P? Oh, well, how do I prove not P? I just do another subproof. This one is just inside the subproof I've already started. How does this subproof work? Well, I just follow my rules. I just say, okay, I'm trying to prove not P, so I just need to assume P, right? I just assume the opposite, and I'm just going to conclude in this contradiction, right? If I can show that P leads to a contradiction, I will have shown that not P is true. And in doing so, I will have satisfied my big subproof, right? I will have shown that assuming not Q really does lead to not P. And that's how I've shown that final thing. Okay, so let's actually do this. So if I have P right here, right? Okay, great. I have my beautiful conditional elimination now, right? Because I have my if P then Q, but I also have my P. When I execute that, I get my Q. But then right away, notice I've got my Q and I've got my not Q. So I can conjoin them. So I'll delete this extra space. So I just need to tape them together, right? I just need to point out what contradiction followed from this assumption. What was the contradiction? Q and not Q. So now, right, I'm good. Because now I've shown that P really does lead to this contradiction. So that must mean in this story, P is actually false. And so what have I actually shown? I've shown that assuming Q allows me to tell this story where P turns out to be false. So what have I done? I've shown that not Q really does lead to not P. But as I did this, right, I needed to do what we call a nested subproof. Inside of one subproof, I needed to construct a new subproof. I didn't get those tangled up, right? I set up exactly what each subproof needed to be, and I didn't let it confuse what the other one was doing, right? And this is generally like how all of these proofs are going to work, right? We need to be very careful about what each rule is doing, what each subproof is doing, and not to let them get mixed up with other ones. As I'm going into something like this, when I'm inside like the middle subproof, right, the super nested one, you can think of these as like Russian nesting dolls, right? And this is the most center one. I can look at the subproof that's outside of me because I'm still like inside that story. It's as if, right, the main subproof is like me telling a quick story And inside that story, I told you another story, right? That's contingent on the big story I've started with. That's how we do these proofs and these subproofs. A lot of times we'll need to set up one subproof, make sure we have all our pieces in order, and then inside that subproof, we might need to build another subproof, right? And it's just important that we're very careful about what level we're on. Okay, so that is negation introduction, right? Also known as proof by contradiction or reduction to absurdity. This idea that you assume something and you show that it leads to some contradiction. And what I just showed in that last example is sometimes those assumptions are going to be nested, right? We might need to already be part of a subproof before we want to create another subproof. That sort of thing is going to come up a lot when we look at eliminating disjunctions. So disjunction elimination is often called proof by cases. So with disjunction elimination, right, it's an elimination rule. So the idea isn't that we're trying to prove a disjunction. We already know how to do that. We already know how to introduce disjunctions. It's what if we already started with a disjunction as a premise? How should I unpack that? And the idea is we're going to think about this as, well, the disjunction is telling me either the left-hand side or the right-hand side is true. So what we'll do is, I don't know which side is actually true, but we'll just say, suppose one side is true, that will lead to the conclusion. And then we'll say, suppose the other side is true, and then we'll show how that will lead to the conclusion. So what do I mean by that? Let's look at this example. So we start with this premise, either A or B is true. We're not sure which, right? It's either A or it's B. We don't know which is true. But we do know that A would lead to C. And we know that B would lead to C. We also know that D is true. So it seems like D and C is going to be true, right? I already know that D is true, and I know that either A or B is true, and either one of them leads to C. So it seems like I'm going to be able to get C. So we need to try to flesh out that intuition. What is it that we're doing that allows us to say, because I know A and B, or either A or B is true, and I know each one independently does what I want it to do, then we're going to get where we want. And that's what the proof by cases is all about. So what we're going to do is we're going to think about this in terms of we have this or statement, and this or statement has a left side and a right side. And the goal is we want to show how both the left and the right on their own are going to lead to this conclusion, right? So this is what we're going to do. We're going to set up two different subproofs. One of the subproofs is going to show how the left-hand side will get to the conclusion, and the other subproof will show how the right-hand side will get to the conclusion. Right? And if I can show that either that both the left-hand side gets to the conclusion and the right-hand side gets to the conclusion, and premise one tells me, oh, I know one of those things has to happen, one of those things is true, then we know where we're going. Right? It's like saying, suppose there's a fork in the road, but each of the forks goes on a bridge that goes to the same town. Right? Well, it doesn't matter which fork you go on. If both bridges lead to the same town, you're going to that town. That's all we mean here, right? There's a fork in the road. We don't know which fork you'll take, which side you'll take, but the point is either one of them, all roads lead to Rome, right, is the idea. So that's what we want to demonstrate here. So we set up this subproof structure here, and that's what OR elimination is all about. Getting comfortable with this setup, that's what it means to get comfortable with OR elimination. Because after that, all we do is we just fill in the blanks, right? Once we have the structure, it's like, okay, well, now we know what we started with, where we're going. So now we're good. Let's just go through our old rules and see how we can do that. So in this case in particular, right, I'm going to assume the left-hand side, and I'm going to show how that gets to the right-hand side, right? So if the left-hand side was true, then, right, I'm assuming A. If A was true, then that must mean C is true, because 5 and 2 in conditional elim, right? Just 2 and 5, right? That's what conditional elim is. And then I can go, right, on line 7, well, then that must mean D and C is true, right? Because all I'm doing is doing a conjunctional introduction. I have C on line 6, D on line 4, and I can just tape them together. So I've shown that one of the bridge gets me to town, right? If I went left, I still get to town. I still get to D and C. And then I just want to set that aside and I want to ask, okay, so what if I went right? Well, still, if I went right, I get C. And simultaneously, if I have C, then, well, cool, I have D and C, right? I'm just doing another and introduction. So what I've done is I've shown that the left-hand side gets me to town, the right-hand side gets me to town. So the point is, because I know premise 1 tells me that you're either going left or you're going right, that must mean that we're going to get to town one way or another. Whether you go left or you go right, you're getting to town. And that's what OR elimination is all about. And it's just that, and that's why we call it proof by cases. You're just saying, okay, I don't know which of these cases will happen, but let's just treat them each independently and show how, regardless of which one happens, they're still going to get us what we want, right? They're still going to yield that conclusion. So like, if I said, I'm either eating chicken or I'm eating turkey today, right? And I want to convince you that I'm eating poultry, right? The idea is that I don't even need to figure out which is true, chicken or turkey. The point is I could say, suppose I eat chicken. Well, because chicken is poultry, it means I'm eating poultry. Or suppose I'm eating turkey. Because turkey is poultry, that means I'm eating poultry. So because you know that I started off with saying I'm either doing one or the other, then you know I'm eating poultry. Right? So that's what proof by cases and OR elimination is all about. So we can look at an example where we use OR elimination, and your clue for when an example is going to require OR elimination is actually, right, not very mysterious. It's just, is a premise an OR? Right? Like, that's not always a surefire way to determine, but like the idea is, again, with elimination rules, you want to be looking, do I have any premises that match that connective? Right? Whereas introduction rules would be thinking, okay, does my conclusion have that connective? So as soon as I see that one of my premises is saying, hey, I don't know which is true, P or Q, then I'm already thinking about this as a big proof by cases. I'm already saying, okay, so what you really want to say is either P or Q is true, and what we want to show follows from that is S, right? And as soon as we lay that out, right, we get the rest of this structure filled in. We're going to try to prove S by showing that it follows from P and it follows from Q. And since we know either P or Q has to be true, one of those has to be true, we know we're getting S one way or another, is the idea. So this is generally how I set up, essentially, nearly any proof that starts with a premise as a disjunction, right? I am almost always thinking, oh, okay, there's a proof by cases here, right? Sometimes that might not be the case, right? Sometimes you might just have another conditional that just says, oh, if P or Q, then R, and then your conclusion is just R, and it's just a very trivial, conditional elimination. But very often, if your premise is a disjunction, and there's no clear way for how you might use that with another statement, often the case is what you should be thinking is, okay, how can I show that either way, either side of this disjunction is really going to get me to my goal? So in this case, right, I just need to show how P will get me to S, and then I'll show how Q gets me to S, and then I'm done. So how does P get me to S? Well, it gets me to R, right? I do my conditional elimination. I grab my P, then R. I grab my P, execute, boom, I have R. Right? And then now that I have R, I can say, oh, well, I know that, again, R leads to S, right? And so now that I have R, right, I can just say, oh, well, so because I have R, I can just do another conditional elimination. I have my conditional right here. R says, right, R leads to S. I actually have R. Boom, I have S. So now that subproof is just done, right? I've shown how P really does lead to S. So the idea is I've shown how the left side really does lead to my conclusion. Now all I need to do is show how my right side leads to my conclusion. So the idea is we're just showing how whichever case occurs, we're still going to be good. And so look at what I've done, right? I've shown that my left side really does lead to my conclusion. Now all I need to do is I need to show that my right side leads to my conclusion, right? So again, I'm just aiming towards S. So what I'm going to do is I'm just going to again say, well, Q leads to R. I know Q is true. So let's say Q leads to R. Q is actually true. So then boom, I know R is true. And now that I know R is true, again, that tells me that S is true because R leads to S. And R is actually true, so boom, S is true. So, and at that point I'm done, right? I've shown that both P leads to S and Q leads to S, and because I know you have to get one of them, that means S has to be true, right? I'm either getting a dog or I'm getting a cat. If I get a dog, I get a pet. If I get a cat, I get a pet. So either way, I don't even care which one it is, I'm getting a pet. I might not know if it's a dog, I might not know if it's a cat, but I still know I'm getting a pet, right? So that's the idea of a proof by cases. We're just separating out. We're given this disjunction. We're told you don't know which one is true. And the point is, we're just showing how it doesn't matter which one's true because both of them will lead to the conclusion. So now let's turn to our auxiliary rules, right? And the idea, like I mentioned, is that these are going to tie up loose ends. So like specifically with or elimination or disjunction elimination, these rules are going to be really useful. So let's start with this argument in particular, right? Suppose we start off with knowing that, well, either A or B is going to happen, but we know that B isn't going to happen. Well, I mean, intuitively, right, it seems obvious. Well, then it has to be A that happens. I'm either getting a dog or a cat. I'm not getting a dog. Therefore, I must be getting a cat, right? If you're told, hey, you're either going left or right at this fork in the road. Oh, but the right side is closed. Well, you know you're going the left side, right? You're either eating chicken or you're eating turkey, but you're not eating turkey. Well, you're eating chicken, right? So like there's something about this argument that's intuitive, but then how do we really unpack this? How do we really explain why this conclusion should follow based on the premises? We might just think, let's set up our or elimination, right? Because the idea is, well, regardless of what happens here, I'm going to be able to justify my conclusion. The first route is pretty obvious, right? What I need to do is I need to show how from A or B, either way, we're going to get to A. I'm going to assume my left-hand side, and I'm going to show how that results in the conclusion. But look at that. The left-hand side just is the conclusion. So what does that mean? That means we use this rule which we call reiteration. And it literally just means you're repeating yourself. So from time to time, it's not going to be that often, but it will happen where sometimes it's just important. I just need to repeat this line again, right? And so specifically, this will happen in these sorts of situations where, hey, in order for or elimination to be happy, you better end the proof with exactly the right line. And so if you already started off with that line, well, then all we need to do is just repeat it. And now, as we'll see in just a moment when we look at the app with all of the highlighting, we'll see like, okay, this left-hand side matches with that, right? This assumption matches with that left-hand side. And then this conclusion here matches with the conclusion down here. So we've shown that the left-hand side yields our conclusion. If A were true, yeah, A would be true, right? But now we want to ask, okay, what if it was the right-hand side? How can we show that that would yield our conclusion? And this is where we get the rule of explosion. The point of explosion is to show what happens if you really did believe in a contradiction, right? So we already talked about contradictions a little bit a moment ago when we talked about how, right, proof by contradiction works, right? If I can show that believing something leads to a contradiction, then I shouldn't believe that thing, right, in the first place. But another way in which we can think about contradictions is, well, suppose just for a bit, we kept on running with this. Suppose for a moment at least, we pretended this contradiction was true. Or, right, we started with this contradiction. Well, remember, a valid inference is one where it's impossible to go from a true premise to a false conclusion. But if you're starting with something that's false, well, then you already know you're not going from a true premise to a false conclusion. So let's put it like this. If we were to bounce back to our truth tables, right, and we were to treat a contradiction as our premise, there would be no way in which we could make that premise true, the contradiction true, but the conclusion false. What that means is literally anything follows from a contradiction. If I believe that I'm a dinosaur, but I'm also not a dinosaur, then we could demonstrate, right, through our truth tables or through these logical rules, why, okay, well then anything follows, right? If you think you're a dinosaur and not a dinosaur, then you believe the earth is flat. So the point of a contradiction is that it would entail anything and everything, right? Let's think back to how we were doing this with our truth tables when we said that an argument is valid, right? The idea was we said, okay, we have some things that we're going to call premises. We're going to call some statements premises, and they entail another conclusion when there's no possible world when the premises are true, but the conclusion's false. But let's just think about any old example with a contradiction. So we can look at this truth table, right, which gives us the truth value of a contradiction, just so we can spell this out, right? And the idea is, here we have phi, and the idea is we have this contradiction built out of phi. So regardless of if phi is true, to say phi and not phi, that's just always going to be false, right? So now let's think about an argument where we say that this thing, this contradiction, let's call that our premise for a second, right? And then we're going to call theta here our conclusion. So one thing we can ask is there any time where these are true, but the conclusion is false, right? Like that was the point of the definition of validity back here, right? We were saying we have a valid argument, a good inference, anytime it's impossible for us to go from true premises to a false conclusion. And the point is, right, when we look at this contradiction, there's just literally never a case when the premise is true, when the contradiction is true. So literally everything follows out of it. So what we can do then is we say, all right, well, if I know that B is true, and I know that B is false, right, from premise 2, then that means I know B is true, and it's not the case that B is true, right? All I'm doing here is I'm just saying 2 and 5 and introduction. But the point is, if I believe a contradiction, I have to believe anything else. Because there is no possible way that this thing is true in the first place. So there's no possible way that this is true while this is false. And that was the only thing we were worried about when making an inference. We were worried about believing something is true, but then jumping to something new that's false. But the point is, that's not a possibility here. There's no way that this could have been true in the first place, so there's no danger of moving from true things to false things. So there's no danger of making our main or our big cardinal sin of moving from truth to falsity. We are already in falsity, so it doesn't matter what else we say, right? So explosion is often like, it feels like a weird rule because it's like, oh, I just get to say whatever I want. But the point is, the only time we're ever going to do explosion is if we're already in a situation in which we know this situation just couldn't have occurred. This is just impossible. This is nonsense. So just like we can say B and not B are both true, we can say whatever else we want because nonsense is going to follow from nonsense. Okay, so this just comes from, right, we say 6 and explode. Right? We just point out the contradiction and we say, okay, because of that contradiction, this thing is, right, I get to say whatever I want. And the reason why I'm saying A follows here is because, again, I'm just trying to be really strict to my rules. For or elimination to work, I need to have one, an or, and then I need to have 2 subproofs. One of them better start with the left side of my or, the A. The other one better start with the right side of my or, the B. And then the idea is I want both the left side and the right side to yield the same conclusion. In this situation, it happens to be A again. So that meant in the first subproof, all I did was do reiteration. I just repeated the A that I already started with. But in the second subproof, right, the idea was this was already, the road was closed, right? This was already an impossibility. So what I was doing was I just demonstrated why this was impossible, and then I said, okay, so if this was already impossible, then anything else is going to follow, in particular, the conclusion that we have in mind. So let's look at the same example, but in our application. right? So the idea is we have, well, either P or Q is true, but P is actually false. So shouldn't we conclude that Q is true? If I'm either getting a cat or a dog, but I'm not getting a cat, well, then it seems like I'm getting a dog. So what I'm going to do then is just this OR elimination, right? I'm going to select what my disjunction is, my OR statement, and then I'm going to say what I want both forks in the road to lead to, and that's Q, right? And so what that's going to give me is, right, two different subproofs, right? I have Q at the very bottom. I'm trying to prove that Q is true. And I'm trying to do that by showing that, well, if P was true, I can show you how I can get Q. And if Q is true, I can show you how I can get Q. The second subproof should be pretty obvious, right? All that I'm going to do is I'm just going to reiterate Q. Boom. Done with the second subproof. It's the first subproof, right, that I need to be a little bit more clever, right? I have P, but oh, look at that. Not P is true. So what do I have? Well, that means that this situation, right, this couldn't have happened. This is already contradictory. So, right, what I'm going to do now is I'm going to point out, here are the things that are contradicting each other, right? And because I have these things that are contradicting each other, I can get whatever I want out. So, right, I get Q in the first subproof by pointing out this contradiction between P and not P. And then in the second subproof, I get Q from just reiterating where I started. But in both of them, right, I took the left side and got to the conclusion, and I took the right side and I got to the conclusion. And that's all that I needed to do. Okay, so that's OR elimination, but that's also, right, we're showing OR elimination while also showing how reit and, explosion work. Most of the time you're going to use reit or explosion, it's going to be within some sort of proof by cases, right? Within some sort of OR elimination. That's not necessarily always the case, but it's a good rule of thumb just to be having in your head that's oftentimes where they're going to be coming up. And with that, that is all of our rules. Now, any valid argument, we have the power to prove, right? So the idea is our elimination rules tell us if I start off with a statement of a particular form, how do I unpack that? How do I squeeze out the information that it's providing me? And then the introduction rules tell us, okay, suppose I want to build a statement of a particular form, right? What is it that I need to do? What is my recipe that would allow me to say A and B are true? Or if A is true, then B is true. And then the idea is with our auxiliary rules, these are just ways of just tying up loose ends. Reiteration just allows us to repeat ourselves. Sometimes, most of the time, that's not going to be very effective, but sometimes we're going to feel the need like, okay, I do need to just have this line popping up over here again based on how the rule is, right, based on what subproof I'm trying to satisfy or something like that. Similarly with explosion, right, this is going to be oftentimes something that happens when you're dealing with a subproof that has an assumption that's somehow contradicting what your premises are, right? If your premises say something like, hey, A is true, and then you assume that A is false, right? We get to a contradiction, and then anything is going to follow out of that. So the idea is, when we're doing proofs, we need to, just like a carpenter is going to be using their tools in the right sort of situations and trying to take, what have I been given? How can I use my tools to manipulate these things and build other things that allow me to build different things? That's the same thing we want to do with our proofs here, right? We want to take these rules and try to apply them to the lines we have and construct the lines that we want to have. But absolutely everything you do in a proof needs to be thought about as going through these rules, right? If you're thinking, if the rules are just secondary, right, then you're approaching this wrongly. So what we need to be doing is always think about what are the rules that actually justify every step we're making. If you really want to be good at proofs, these need to be second nature, right? Just like when you're doing like arithmetic, you don't look up like, what does plus mean? How do I deal with that, right? You definitely don't want to be looking up, how does conjunction introduction work, right? Like something like conjunction introduction, right, should be really second nature. And by the end of talking about all these proofs, hopefully all of these rules become second nature, right? This idea of, hey, if I need to eliminate a conditional, I just need to find the left side and that'll give me the right-hand side. Or if I need to create a conditional, oh, I just need to build a subproof that demonstrates how that left-hand side would lead to the right-hand side. So hopefully these things are becoming more internalized. Really, the best way to do that is just to be doing more and more examples. And that's one of the big reasons why I've built you the app in question, right? So that way you can just keep going through example after example, and you can see like, okay, it's not liking when I do this, but it's allowing me to do that. And as you go through that, you'll begin to really see what the spirit of the rules are, right? By the end of this, you definitely don't want to be forcing yourself to go look at, right, the technical details. They really should start to become just second nature. All right, so that's it for proofs. Again, this is a real core part of almost every logic class, so it's a great thing to spend extra time on and to internalize, especially if you're going forward and using any sort of math or science or computer science or whatever in your future. These sorts of proofs and thinking about this, not just I understand the rules, but like you understand how to approach things in a proof-like mindset is going to be really beneficial. And aside from our super technical things, right, just learning how to think about things in proofs can just make it much easier to communicate with other people, right? So often when I'm trying to explain to someone how I think about something, I just want to slow it down and make it so, okay, let me just first articulate what my starting points are. And then let's just treat each step really slowly and innocently. So that way we know whether or not there's any weak links in the chain. And if we can agree that there are no weak links in the chain, then we can both be confident in the conclusion. All right, take care out there and stay safe.